Shalom and welcome everyone. I want to thank you once again for joining me on Checkpoint Training Bytes. Checkpoint Training Bytes is where we bring advanced training on checkpoint products, features, and blades. In this video, we'll be discussing VRRP and VRRP solutions. But before discussing VRRP, let's take a few moments to discuss the agenda of this module. The first thing we're going to discuss is why you need clustering and what are some of the clustering solutions out there. The next thing we're going to discuss is VRRP, why VRRP was created and what its purpose is. Third, we're going to take a look at and define the different VRRP configurations. And specifically, we're going to discuss the VRRP version 2 and also VRRP monitored circuits. And then we're going to take a look at the VRRP protocol to define exactly what it does and what's contained in the VRRP packet. And then we're going to define all the different VRRP monitored circuits components and their definitions and how they are used. And then finally, we're going to take a look at some additional VRRP terminologies, what these terms are and what their functionality is. And so before discussing VRRP, let's take a few moments to discuss why you would need to have VRRP. And so let's take a look at some other solutions instead of VRRP. And now primarily, I've seen customers use dynamic routing to redistribute the load in case of a network failure. And so some customers will use dynamic routing like OSPF and RIP. And so dynamic routing will point all the routes to a router. And if that router should ever go down, dynamic routing will recognize that there is a dead route or a black hole. And then it will update all the routers and find the next best available path. And so in this case, it will send all the packets to the secondary router in order to get out to the internet. Now this solution is valid in a sense that it works. But there is a problem with this solution. The problem is that while the routers are sending updates and reconverging and looking up the new path, packets are getting lost. The packets that are being sent to the primary router are actually being sent to a black hole, a dead route. And so all these packets are being dropped. All the packets from the inside to the internet and from the internet back to the internal network, they're all being sent to the primary router, and that router has a dead route. And so all those packets will be dropped and discarded. And so there is about a minute or two before the routers decide on the next best path. And during that minute or two, there is a lot of packets that are being dropped. And so even so, this is actually a valid solution. It's not the optimal solution. And so that's why we came out with a better solution. VRRP is an industry standard solution available for everyone out on the internet. And so not only Checkpoint runs VRRP, but other vendors like Nokia, Cisco, Juniper, etc. So Checkpoint has two clustering solutions. Number one, we have a clustering solution called Cluster XL. It's a Checkpoint proprietary clustering solution. And number two, we have a VRRP clustering solution, which is an industry standard clustering solution. In the previous video, I discussed Cluster XL, and now in this video, I'm going to discuss VRRP. The Cluster XL clustering solution offers us two methods of clustering. First, we have the high availability solution, which is an active standby solution. That means that one machine is active passing traffic and all other machines are in standby mode, which means that they are passive and they're not actually passing any traffic. In case the active machine goes down, the passive will promote himself to active. The next Cluster XL solution is the load sharing solution. In the load sharing solution, all machines are in active status. That means that all machines are actively passing traffic simultaneously and at the same time. And then we have VRRP. VRRP is primarily known as a high availability clustering solution, which again is where we have one machine that's active status and it's passing all the traffic, and all the other machines are in passive status and they're not processing traffic until the active machine goes down. And then one of the standby machines will promote itself into active and then start processing traffic. Also, there is a possibility to configure VRRP in the load sharing solution, but this solution has some limitations. And so if you really need to do load sharing, best practice is to use Cluster XL in the load sharing solution. And so in this video, we'll be discussing VRRP in a high availability solution. But first of all, let's define what VRRP stands for. VRRP, also known as VRRP, stands for Virtual Router Redundancy Protocol. And so VRRP is defined in a few RFC standards. RFC stands for Request for Comments. which are Internet standard documentations that define how protocols should behave out on the Internet. And so there's a few RFCs that define how VRRP works. There is RFC 3768, which defines VRRP version 2, which is an IPv4 solution. And there's a new and enhanced update to this RFC. There's RFC 5798, which is also known as VRRP version 3. And this RFC supports both IPv4 and also now IPv6. In this video, we're only going to talk about IPv4. We're not going to discuss IPv6. But in addition to discussing VRRP version 2, we're also going to discuss a new enhancement to VRRP version 2, which is what we call VRRP monitored circuits. And VRRP monitored circuits address some of the flaws and issues that Check Point found with VRRP version 2. And so Check Point has deviated a little bit from the original VRRP version 2, but it used VRRP version 2 as the backbone, and on top of it, it enhanced it and improved it, and which is what we call VRRP monitored circuits, which is basically VRRP version 2 with some new enhancements and improvements. And so VRRP is supported on 2 of Check Point's operating systems. It is supported on Gaia operating system, and it's also supported on IPSO operating system. But you cannot run VRRP on Splat operating system because it's not built into the operating system's code. IPSO operating system is being deprecated, so in a few years it will no longer be supported. And so on this video I'm going to focus on VRRP on Gaia. And so what is VRRP? As mentioned already, it's a redundant routing protocol. And that basically means if you have an active firewall and that active firewall goes down, then you want to have redundancy built in. And so you have a backup firewall to redistribute the load out to the internet. And so basically you will never have a complete network outage because you always have redundant backup firewalls backing up the active firewall. And so if the active firewall ever goes down, you have a redundant backup firewall to take its place. And this VRRP failure detection routing mechanism will be triggered within sub-seconds instead of minutes, like the dynamic routing example I showed you earlier. And so it will have either minimal or absolutely no network interruption during the failover transition. And now that we understand the need for VRRP, let's discuss exactly how VRRP works. And so let's first take a look at VRRP version 2. And so in this scenario, we're going to have 2 firewalls. And so 2 firewalls are going to be part of this cluster, but you can have more firewalls part of the cluster. And so one firewall is going to be the master, and the other firewall is going to be the backup. In VRRP, we don't use the terminologies active standby. We only use the terminologies master backup, which basically means the same thing. And so all traffic is going to be forwarded to the master machine. And so the master machine is going to be the one that's going to process the traffic and forward the traffic out to the next destination. And the backup firewall is just a passive machine. He's just passively waiting until that master machine goes down, and once the master machine goes down, that backup machine will promote itself into master status. And now the new master will be the one responsible for processing the traffic and forwarding the traffic out to the internet. But I'm getting ahead of myself, so let me back up just a little bit so I can explain something else. And so all traffic from the internal network are pointing to a default gateway of .1. And so in this case, the master owns the IP address of .1 and the backup owns the IP address of .2. And so all traffic is being forwarded to the gateway of .1, which in this case is the master firewall, which again will process the traffic and forward that traffic out to the internet. Now in case that the master machine goes down, not only does the backup transition into the new master state, but it also transitions and owns the original master's IP address of .1. And so .1 is actually what we call the VRRP backup address that floats amongst the members, and whoever is the master owns the IP address of .1, which is the VRRP backup address. And so all traffic is still being forwarded to the default gateway of .1, which in this case is the new master machine, who now owns the IP address of .1. And not only does the new master owns the original master's IP address, but it also owns the MAC address. So the MAC address of the original master also gets transitioned into the new master's MAC address. And so no ARP entries need to be updated. And so all traffic that was forwarded to the original master's MAC address is still being forwarded to that MAC address, which is now owned by this new master's machine. Now, before I go too deep into VRRP version 2, let me just pause here and talk about a few issues. First of all, VRRP version 2 is only supported on IPSO operating system. It's not supported on Gaia operating system. VRRP version 2 had some design and implementation problems. And so that's why Checkpoint came out with VRRP monitored circuits, which address some of these design flaws. And so that's why Gaia only supports VRRP monitored circuits and does not support VRRP version 2. And what are these design flaws? Well, there are a few of them, but the main one is that the whole box had to fail in order for VRRP failover to occur. And so we ran into certain situations where only an interface failed. And so if only an interface failed, the box will still stay up as master and processing traffic, even though there's an interface that's down. And so if only one interface fails, the VRRP will not completely fail over. And so actually, all traffic is now being sent to a black hole, meaning that packets are being sent to an interface that's up, but it cannot obviously be processed by the interfaces that are down. And so this traffic is being lost and not being forwarded. And so this is what we call a black hole. And this can cause a complete network outage. And so in order to resolve this, we had to enable dynamic routing like OSPF. And so when OSPF detects that an interface has failed or there is a dead route, OSPF will learn about the next available path and then forward the traffic out through the secondary router. And so this situation can lead us back to the previous problem that I mentioned before, where dynamic routing like OSPF will take too long to identify that there is a dead route. And so it might take a minute or two before it's able to figure out what is the next best available path to forward the traffic through. And so Checkpoint came out with VRRP monitored circuits, which address this design flaw by having each interfaces monitoring each and every other interfaces. And so if there is an interface that goes down, the interfaces that are monitoring it will actually also go down, which will then cause a complete failure of the box, which will then trigger VRRP failover. Another VRRP version 2 design flaw was that the floating MAC address can actually cause issues on the switches when it fails over. And so if the switch sees two ports with the same MAC address, it thinks that there is a loop, a broadcast storm, and so it's going to shut down one of the ports, which can cause a network failure. And so in VRRP version 2, if you have two firewalls, you only have two IP addresses, the master's IP address and the backup's IP address. And so you decide which IP address you want to be the floating IP address. And this floating IP address in VRRP version 2 is called the backup address. And this backup address will be the address that you decide that you want to be the master. And so when the master machine goes down, this backup address will also float over to the new master machine, and so all traffic will be forwarded to the new master's backup address. And so this MAC address can cause some issues because it will be seen by two ports on the switch. And so to address this issue, VRRP monitored circuits designed a virtual IP address and a virtual MAC address to be the floating IP address. So this third IP address is a virtual IP address that will float amongst the members depending who the master is. So all traffic is going to be forwarded to the virtual IP address, and whoever is the master will own the virtual IP address, and he's going to be the firewall that will process that traffic. So if the master goes down and the backup becomes a new master, this virtual IP address will float over to the new master machine. And so not only does the new master own the virtual IP address, but he will also own the virtual MAC address. So all traffic is going to be forwarded to this virtual MAC address, who is now the new master, that also owns that virtual IP address. And so now the next thing I want to talk about is the VRRP protocol. What exactly is the VRRP protocol? Well, when machines are configured to run VRRP, the VRRP cluster machines will be sending VRRP multicast packets between each other. And so when a cluster first comes up, all machines will be sending VRRP hello packets between each other. And so the first machine that comes up, he will become the master. But let's say there's more than one machine that comes up at the same time. And so these VRRP hello packets will be sent amongst all the machines. And then they're going to make an election process to determine who is going to be the master. And usually it's the machine with the highest IP address that becomes the master. And after the VRRP election process is completed, only the master machine will continue to send VRRP hello packets. All the other machines will stop broadcasting VRRP hello packets. They will just be passively listening while the master broadcasts the VRRP hello packets. And so the backup will stop sending VRRP hello packets to reduce network congestion. But then only when the master machine goes down and it stops sending VRRP hello packets, and then the backup machine will recognize that there is an issue with the master, and he will now start broadcasting VRRP hello packets so he can become the new master. So now let's define VRRP monitored circuits so we can have an understanding how it works and how to configure it. And now the first thing you need to configure when you configure VRRP is a virtual router ID. The virtual router ID is just a number between 1 and 255. So you arbitrarily just pick a number between this range. And all the machines that are participating in their VRRP cluster should have the same virtual router ID number. And so the machines will know if they participate in the same VRRP cluster if they have the same virtual router ID number. The virtual router ID number will be sent inside the VRRP multicast packets, and only the machines that participate in the same virtual router ID will be able to process those packets. And so you can have multiple clusters, and each cluster will have a different virtual router ID number. The next thing you need to define is a priority. The priority is just a value between 1 and 254. And here you can define which machine will have the highest priority. Now you could arrange to have both machines to have the same priority. And so if you do that, during the election process, the one with the highest IP address will become the master. But I'd like to define, and it's also best practice, to have different priorities on all the machines that participate in a VRRP cluster. And so the priority will be higher on the master and lower on the backup system. This prevents VRRP from flapping, which basically means that the cluster will not be fighting for VRRP mastership status. And so to start off with, I like to define a higher priority on one of the machines that I would like to become the master, either because it has the more powerful CPU and processor, or if they have the exactly same hardware, I just arbitrarily pick one to become the master and give it the highest priority. And so in this case, I'll give the priority of 100 on the master and a priority of 95 on the backup system. And so the VRRP hello packets will not only send the virtual ID number, but also will send the priority value. And so during the election process, the one with the highest priority will obviously become the master machine. And now the next value that you need to define is the delta. What is the delta? The delta is a value that the cluster will subtract from the priority in case of an issue. But the delta will only be invoked if there is an issue. And so if there is no issue, the delta will not be subtracted from the priority. But if there is an issue, the delta will be subtracted from the priority, which will give us what we call the effective priority. And so the effective priority is that true priority at that moment in time. And so the delta is a mathematical number between 0 and 255, and it's a mathematical number in relationship to the priority. And so when you subtract the delta from the priority, you'll get the effective priority, which is a value that will mathematically make sense. But if there is no issue, the delta will not be invoked, so the effective priority will stay as the base priority, which is 100. And so in this case, the priority of the master is 100, and if there is an issue, it will subtract the delta, which will give us an effective priority of 90. And so since the effective priority on the backup is 95, because he does not have an issue, and so then who becomes the master is the one with the highest priority. In this case, it's the backup with a priority of 95. And so when the master sends VRRP hello packets, his priority is 90, and the backup will recognize that he has a higher priority, and he will start advertising VRRP multicast packets. And the original master will recognize that there is now a new master, and he will back down into backup state since it now has a lower priority. And so this process can go on. And so if there is an issue on the backup will subtract the delta from his priority, which gives us an effective priority of 85. And so he will start advertising his effective priority as 85, which will cause the original master machine to start advertising because he has a higher priority of 90, which will make the new master machine back down into backup state because he has a priority of 85. And so the original machine will promote himself into the master, and this machine will demote himself back into backup state. And so this process can repeat itself on and on until they can no longer participate in the cluster when their effective priority is down to 0. And so when the machine effective priority is 0, he will actually remove himself from the cluster and will no longer participate in the cluster. And so he will no longer send VRRP hello packets. In fact, if any machine needs to leave the cluster for maintenance, he will send his effective priority down to 0, which will notify all the machines that he's going to be leaving the cluster. I briefly discussed the VRRP protocol, but now let's go a little bit deeper and further in discussing the VRRP protocol. So to start off with, let's take a look at the VRRP protocol and actually take a look inside the VRRP packet. Inside the packet, the first thing you will notice is the source IP address. The source IP is the original host that's sending this VRRP packet. And then the next thing you'll see is the destination IP address. And so note that it's a multicast IP address. 224.0.0.18 is a reserved multicast IP address that's reserved for VRRP protocol. The next thing you'll note is the IP protocol number, which is 112, which is again a reserved IP protocol number for VRRP. And now you'll note the virtual ID number, and this will be the virtual ID number that you define for your cluster. And so in the previous example, I used virtual ID 50, and so this is what you're seeing here. And the next thing you'll see is the priority, and the priority is what you define for your VRRP machine, or the effective priority that the machine is currently at. And then the next thing you'll notice is the time to live. According to the RFCs that I talked about earlier, the time to live should always be equal to 255. What that means is that you cannot have a router in between the VRRP cluster, because if the VRRP packet is transversing the router will decrement the time to live by 1, and so when the VRRP packet arrives on the VRRP member, it will recognize that this is an invalid VRRP packet, and so if the time to live is not equal to 255, according to the RFC, the VRRP members must drop the packet. And so there's a few terminologies I have not explained yet, so let's take a few moments to explain these new VRRP terminologies. The first term I want to explain is the hello interval. The hello interval refers to how many packets are sent during a certain time period. The VRRP hello interval is set to 1, and I do not recommend to change this value. Now this value refers to the VRRP hello packet, so in this case every 1 second it will send a VRRP hello packet. And so every second a VRRP hello packet will be sent, which defines the virtual router ID number, the priority, and also the time to live, which is destined to the multicast IP of 224.0.0.18. And now the next terminology I want to define, and it's related to the hello interval, is what we call the dead interval. The dead interval refers to how many packets need to be missed before the cluster recognizes that there is an issue and then needs to take action. The dead interval default time is set to 3, which means 3 packets need to be missed before the firewall realizes there is an issue and then needs to take action. And so it's not recommended to change the dead interval time because both the dead interval and hello interval are interrelated. So even though I'm saying not to change these values, I'm going to give you an example where I actually change the values so you can have an understanding of how they interrelate. So if I change the hello interval to 2, that means that every 2 seconds a VRRP hello packet will be sent. And if I kept the dead interval at 3, that means that 3 packets need to be missed. And so in total that will be 6 seconds before the VRRP cluster will fail over. And so as mentioned, it's best practice not to change these intervals. Now in a computer world, in the internet world, 3 seconds is a long time to trigger a failover. A lot of packets can be missed in 3 seconds. That's a long failover time. And so this was also another VRRP version 2 design flaw. And so VRRP monitored circuits addressed this problem by introducing a new metric parameter called the Skew time. The Skew is a mathematical formula that determines how fast packets are sent and how fast failover transitions occur. Now I don't want to get into the math behind the Skew formula, but suffice to say that the higher your priority is, the faster packets are being sent and the faster transitions will occur. The lower the priority, the slower the packets will be sent and the slower the failover transitions will occur. And so think of the Skew metric as a value that determines how fast transitions will occur. And so instead of hello packets happening every 1 second and dead intervals happening every 3 seconds, think of it as intervals. There will be 3 packets being sent in a certain interval, and after 3 intervals, the failover will occur. And also I want to point out that the higher priority is, the faster the packets will be sent, which can actually cause some network congestion problems. And so my suggestion, and probably best practice, is to keep the priority of 100 on your master, which ensures a quick failover, but also a low packet overhead. And now the next thing I want to talk about is authentication. When you define VRRP, it asks you if you want to use authentication. And you can set it to none or set it to simple. And so none requires no password, and simple requires a password. And so only the machines that are part of the same virtual ID and have the same password will be able to process the VRRP hello packets. And now the next term I want to discuss is the cold start delay. The cold start delay defines how long it will take for the machine to participate in the cluster. Then the question is, why would you want to delay how fast the system joins the cluster? And so in order to answer this question, we have to look back a little bit at the history of VRRP. And so when VRRP was created, it was created for routers. And so when routers first come up, they can automatically start participating in a VRRP cluster. But now we're setting up VRRP not on routers, we're setting up VRRP on firewalls, which at its core is still a router. And so when the router comes up, it can join the cluster. But you don't want the firewall to join the cluster right away, because the firewall services might not be fully loaded before the machine joins the cluster. And so if a firewall joins the cluster and the firewall processes are still down, it can actually cause a network outage. And so by increasing the cold start delay, you're allowing the operating system to load, the routing daemon to load, the firewall services to load, and the firewall policy to install. And so when the firewalls are fully loaded and synced with the members, now they can join the cluster. And so the cold start delay is just basically allowing some time for the firewall services to load before it joins the cluster. And so just to be sure this is clear, let me give you an example. And so in this example, assume we have a master machine and the master machine needs to be rebooted. And so we reboot the master machine, and obviously the backup machine will recognize that the master is down, and so the backup promotes itself into master state. Now as the master machine is rebooted, and so it's going to load the operating system, it's going to load the checkpoint services, and it's going to load the firewall policy. And so only after the cold start delay has expired, and I recommend 30 or 60 seconds, in some extreme cases I've seen it up to 120 seconds, and only after the cold start delay has expired will the machine join the cluster. But note that there is already a master in the cluster, and so when this machine fully loads and starts to join the cluster, it's going to preempt the existing master, and now he will become the master. Now the terminology preempt is what I want to discuss next. And so when a machine recognizes that he should be master, but there is already existing master for that cluster, he's going to preempt the existing master. He's going to kick out the existing master by becoming the master with a higher priority. And so because he has a higher priority, the other machines will recognize they have a lower priority and they will go into backup state. And so preempt is something that you can enable and configure. Why would you want to configure this? Let me give you an example. And so assume that the master goes down for whatever reason, and the backup then becomes the new master. And so when the original master comes up, he's going to recognize that he has a higher priority and will try to preempt the new master. And so in some cases it's not recommended to preempt the existing master because that can actually introduce some issues. Because VRRP on the routers can fail over and fail back, but now on a firewall it's designed to fail over but not really designed to fail back. And so when you have an original master and he fails and the backup machine becomes the master, when the original master comes up, the new master will not be syncing to the original master, because usually VRRP is syncing from a master to a backup, not from a master to a master. And so sometimes if the original master goes down, you don't want him to come up as the master. You might need him only to come up as the backup, and so that the new master will sync to the original master who is now the backup. And so you can disable the preempt option to disable this from happening. And so now we come to the end of the video. So let's take a few moments to summarize everything that we discussed during this video. So to recap, we discussed why you need clustering solutions, and we also discussed that Checkpoint has two clustering solutions. We have a ClusterXL clustering solution, which is a proprietary clustering solution. And we also have VRRP, which is an industry standard clustering solution. And so we have two kinds of VRRP. We have VRRP version 2, which is an industry standard clustering solution that's documented in RFC 3758, but it's mostly designed to run on routers. And then we have an enhanced version of VRRP, which is what we call VRRP monitored circuits. So monitored circuits address some of the flaws and fix some of the issues that VRRP version 2 had. And VRRP version 2 is an industry standard that will run on multiple vendors and multiple operating systems, including Checkpoint's IPSO operating system. But unfortunately, it will not run on Gaia operating system. Only VRRP monitored circuits will run on Gaia operating system. And that's because there's a few issues with VRRP version 2, including some implementation problems when running on the firewall. And so that's why Checkpoint came out with VRRP monitored circuits, which address some of the issues and flaws with VRRP version 2. And so VRRP monitored circuits will be able to run on Gaia operating system, IPSO operating system, and has some enhancements and some improvements that will make it run perfectly on a firewall. And we discussed a little bit of VRRP version 2 configuration, and I mentioned that you can have 2 or more firewalls in the cluster, and each of the machines are going to have their own individual IP addresses, and one of these IP addresses needs to be selected to be the backup address, and that's the address that all the machines will be pointing to as their default gateway. And so if there's a network failure, the machines will still be pointing to the same default gateway, so there will be no network interruptions. And so that backup address is a floating IP that will float amongst all the members depending on who the next master machine will be. And we also mentioned that there is a backup MAC address that will also float over to the new master machine. And so not only do you have a backup IP address, but you also have a backup MAC address, and so both the IP address and the MAC address will float over to the new master machine after a failover. And so after a failover, all traffic will still be forwarded to the same IP addresses and the same MAC address, which is the original master machine's IP address and MAC address. And so this will guarantee a seamless failover to a new master machine that now has the same original MAC address and the same original IP address. And so in essence, it's like having duplicate machines with the same IP addresses and the same MAC addresses. As a machine fails, the backup machines will take over with original IP addresses and original MAC addresses. And so then we talked about VRRP monitored circuits, and you can have 2 or more machines in the cluster, and each of the machines are going to have their own IP addresses and MAC addresses, but in addition, you're going to have a virtual IP and a virtual MAC address, and whoever is the master is going to own these virtual IPs and virtual MAC addresses. And so then all the internal hosts are going to have the default gateway as this virtual IP address and also have the virtual MAC address. And so all traffic is going to be sent to this virtual IP, virtual MAC address, and whoever is the master is going to process that traffic. And if the master machine goes down, the backup machines will take over the virtual IP addresses and the virtual MAC addresses. And so all traffic is now being forwarded to the new master machine, who now owns the virtual IP address and the virtual MAC address. And then we talked about the VRRP protocol, and the VRRP protocol is the heartbeat of the cluster. When the machines first come up, they're going to participate and send VRRP hello packets to each other. And so in the beginning, they'll be sending VRRP packets amongst each other to determine who is going to be the master. And once the election process is completed, the master will continue to send VRRP hello packets, and all the backup machines will stop sending VRRP packets to reduce network congestion. And then we discussed the information that's contained in the VRRP multicast packet. And inside the VRRP packet, there's going to be a few information like the source IP address, which is the host that's going to be sending the VRRP multicast packets. And then the destination is going to be to the multicast of 224.0.0.18, which is a reserved VRRP multicast IP address. And the packet will also contain the virtual router ID number, the priority of this member, and the time to live, which should always be equal to 255. And the other thing that we talked about is the VRRP monitored circuits, all the configuration components that you need to configure. And we mentioned that you need to configure the virtual ID number, and the virtual ID number defines who the cluster is and what machines participate in that cluster. And then we also defined the priority, and each machine should have different priorities, and the one with the highest priority will be the master. And then we talked about the delta, and the delta is a mathematical number that can be subtracted from the priority in case there is an issue. But this delta will only be subtracted if there is an issue. So if there is no issue, the effective priority will equal to the priority, but only if there is an issue, let's say an interface goes down, it's going to subtract the delta from the priority, which will give you a lower effective priority. That should be lower than the backup machine, who will then become the master. And then the last thing we talked about, it was some of the VRRP terminologies and their definitions. For example, we talked about the hello interval, and the hello interval defines how many packets are going to be sent. And so every second or every interval a packet will be sent. And this parameter defines the VRRP heartbeat, which determines how many packets will be sent for the VRRP heartbeat keep alive. And the next thing we talked about is the dead interval. And the dead interval defines how many packets need to be missed before the backup machine determines that there is an issue and then takes over the mastership state. And the other thing that we talked about was the skew, and the skew is just a metric, it's a formula that defines how fast that packets will be sent and how fast failover transitions will occur. And the skew is based on the priority that you defined on your cluster. And so the higher your priority, the faster packets will be sent and the faster failover transitions will occur. And the lower your priority, the slower VRRP hello packets will be sent and the slower VRRP transitions will occur. And then we talked about authentication, and we defined if you wanted to have a password when you're setting up VRRP. And one of the options is to set it to none, which does not require you to set up a password, or the option to set it to simple, which does require you to have a password. And so when these hello packets will be sent, only the machines that have the same password will be able to process those packets. And then we talked about the cold start delay. The cold start delay is just a parameter that defines how long you want to wait before the system joins the cluster. And one of the reasons you might want to wait is you want to be sure that all the checkpoint firewall services are up and running before the system actually joins the cluster. Because the last thing you want to do is have the system join the cluster and the firewall processes or some of the daemons are still not up and running, which can cause some network outages. And so you can increase this cold start delay from about 30, 60, or 120 seconds, depending how long you might want to wait before the system fully joins the cluster. And then finally we talked about the preempt mode. And the preemptive mode just basically defines if your original master machine goes down and as it boots up, do you want him to come up in the master state or do you want him to stay in the backup state? And so in some cases when the original master comes up, even though it has the higher priority, you might want to keep him in the backup state to prevent a network interruption or possibly a network failure. And so what you want to do is turn off preempt mode, which prevents the original master machine to come up in master state after a reboot or a failure. And so that's pretty much all the information that we covered in this video. I hope you found this information informative. Once again, I want to thank you for joining me in Checkpoint Training Bytes. And so I hope to see you again in the next video. But until then, I want to say goodbye and shalom.
Checkpoint. We secure the future.